Okay, so I should start then. Yeah. Okay, so thank you, Desilava, thank you, Boyana, thank you all the Pangeos team for inviting me to do this talk about thermal remote sensing for crop monitoring, crop water requirements, and water stress across scales. My talk today will be organized in these points. I will start with the rationale of using thermal sensors to assess water stress and the objectives of this webinar. Then I will show you some tools, some products that I have been using during my career for measuring water stress with thermal sensing. Then I will focus more on one specific index, the crop water stress index, its concepts and different methods to calculate it. Then if I have enough time, I would like to show you some results of my research using these tools and how we can validate them with physiological or biomass parameters and how they are consistent across different scales. And the last point will be just some decision support examples that are based on thermal imaging. And of course, I will finish with some take-home messages. So starting with these objectives, probably many of you already know that the plants, when they have enough water, they open the stomata, and then when the water goes through the stomata, that triggers an evaporative coolings, which is translated into a lower canopy temperature. In the contrary case, when the plant has a problem or has not enough water, then they close the stomata, stomatal closure occurs, and then the transpirations decreases, increasing the canopy temperature. For example, what we can see here, I hope you can see my laser, is a green RGB image with, in this case, is a garlic plant with wet and dry references. I will explain later why I use those references. And in the RGB image, we cannot see many differences, but when we move to the same thermal image, we can see how the wet references, the wet leaves are with a lower temperature, the dry references are with a higher temperature, and the plant is between those two temperatures. So the objectives today is to understand water stress based on thermal indicators, to compare the tools and how they can be used at different scales, or which one are best applied in different scales, and also to translate these thermal measurements into specific decisions. So moving to these products and tools, I have classified them in 4 groups. The first one would be the handheld thermal cameras, but also the infrared radiometer sensors. These ones are used for ground measurements. In this case, the high precision infrared radiometer can be used also to calculate or to measure emissivity. Then we have thermal sensors mounts on drones, on UAVs. Another group would be the satellite images, the thermal images, or even the products that some missions like EcoStress could bring us, just with already calculated water stress indices. And one would be the surface energy balance models that combine both thermal measurements with in situ measurements with, for example, a leaf area index, meteorological data, fractional cover, or whatever. So about the handheld cameras, they are really good for visual inspection because they allow for the separation of the vegetation from the ground, from the soil, or whatever in the same image. For example, we can see here in a paper that we published in 2019 with Miguel Costa, we can see 2 RGB images and 2 thermal images. In the wet date, we can see in the thermal images differences in the soil with the shades and with the under sunny conditions. But one interesting thing is that we can see also the irrigation bulbs. But the most interesting part here is if we move to the dry date, we can see also these differences in the soils, but also in the canopy. We can see here, if we focus here, how the lower part of the canopy has higher temperatures than the upper part of the canopy. And this allows us to differentiate physiological performance on the upper and lower part of the canopy in a vineyard, but also on the berry quality. Another example is this one from my thesis. This is also another published article. Is the same example as I showed you before. This is a methodology we will see later to calculate crop water stress index, and with that we can do cultivar screening, we can do irrigation scheduling, we can calculate different water status related parameters that could allow us for decision making. About these kind of tools, the infrared radiometers, we have this kind of handheld ones. For example, these ones I use for ground measurements while I'm using the drone. What we see here is the sensor. So this kind of tools has a specific field of view, and they are very high throughput, so they are very easy to use. But the problem is that they give you the average temperature of the target that you are measuring within that specific field of view. So they do not differentiate between soil and canopy. You cannot differentiate that because you are measuring all the target that is under that field of view. But they are really useful for example, as I told you, for calibration of drone temperatures with drone temperature. If we measure the same points that the drone is measuring with this on the ground, we can then do an empirical line and calibrate the temperature of the drone to ground temperature. And also, these ones can be connected to data loggers. For example, here we have them connected to data loggers in a tower, and they can give you continuous monitoring every 5, 15, 30 minutes. So with that kind of measurements, you can calculate, for example, the non-water stress baseline that I will explain later. So they have many advantages, but also some limitations. About the thermal cameras and sensors mounts on UAVs, on drones, of course, the main advantage is the extensive coverage that we can measure with them. So with the drone, we have the ability to cover an entire plot of, for example, this one is around 10 hectares in just 20, 25 minutes. Also, the accessibility. Imagine to measure one by one or plot by plot in a big area, for example, in a maize farm, that is challenging to go through it because of how tall is the plant. I'm using the example of maize, but this can be said for many other crops. So the accessibility is another advantage of the drones, and the automation. The thing that the images are geolocated and that you can distinguish very easily the plants allow you for precision agriculture purposes. Disadvantages, of course, they have disadvantages. One of the main disadvantages is the high initial cost. They are not, they are expensive actually. If you want a good sensor with a good drone, you have to do an investment. Also, the regulations, national and international regulations in some specific areas. For example, in Albacete, where I live, we have a military zone. So many areas around, we cannot fly the drone. Also, the weather conditions, we cannot fly the drone under high wind speeds or, of course, rainfall or whatever. And also the technical expertise. Nowadays, to fly drones is somehow easy because it's almost automatically done. You can just press some buttons and then you fly the drone. But the post-processing and the processing of the images is not so easy. So the technical expertise is needed. About the satellite images and products, we can easily download thermal images for post-processing, or even some stress-related already calculated indices. For example, ecostress give us some indices already calculated in some areas. So the advantage is it's quite easy to understand. So they allow for, sorry. So they allow for historical monitoring, and they can coverage large regions. Disadvantages, I would say that the main disadvantage of satellite images is the resolution. The resolution scores is 100 meters for Landsat, 300 meters for Sentinel. EcoStress has a somehow good resolution, 70 meters, but the time scale is not good because they do not repeat like the same dates or the frequency. So you sometimes have a lot of images, sometimes you don't have. And of course, another disadvantage is the cloud cover. The good thing is that new missions are going to be launched soon. For example, the Trisna one, that is made by the Indian Space Agency also with France, or the LSTM in Europe, that they will be launched soon. Trisna, I think this year or next year. LSTM, I hope before 2030. But we will have higher resolution soon. And finally, the surface energy balance models. Now we are using a lot the two-source energy balance models and the simplified two-source energy balance models. They use thermal measurements, but also optical or biophysical measurements, meteorological measurements. And the good thing is that they allow you to calculate actual evapotranspiration. So they provide water consumption or water use directly. So that is very useful. But also they have a technical complexity. We need to understand how they work and the algorithm. And you need also some specific local inputs, especially meteorological data. Another way to refine the scale of thermal images is to use disaggregation techniques using optical data and their physical relation with thermal data to refine a spatial resolution. So this is a summary of the different technologies or tools that we can use at different scales, the main advantages or disadvantages. I'm not going to read them again, but if any of you are interested on the presentation, of course, I can share with you. So let's move to the crop water stress index, its concept and the different methods. The crop water stress index is used to normalize the delta T. The delta T is the difference between canopy temperature and air temperature. Of course, if we just measure canopy temperature, it will depend on the air temperature. And if we use just delta T, it would be good enough if the VPD is constant, if the dates have the same VPD and the same air temperature. But of course, this changes a lot. That's why we need to normalize this delta T with the crop water stress index. There are different ways to calculate the crop water stress index. I will talk today about two that I have used a lot. So the first one, sorry, is the one that use artificial or not artificial or natural references. This T-wet means the temperature under wet conditions, or the T-dry, the temperature under non-transpiring canopy. So this would represent the T-wet, or the lower limit based on the empirical method, would represent a maximum transpiration canopy, and the T-dry, or the upper limit, would represent the non-transparent canopy. With these formulas, you obtain a crop water stress index between 0 and 1. 0 means no stress or maximum transpiration. 1 means maximum stress or non-transparent canopy. So there are different methods. The empirical one is the one that I am using more, that is related with this formula. You need to construct an empirical line, the non-water stress baseline, that is based on the response of delta T against PPD. I will show you now how to do it. The theoretical one, that is usually using surface energy balance models, and the one using reference baselines, that I am also to talk about it now. So about the one using wet and dry references, you can use different references, natural or artificial ones. The natural ones would be perfect, would be if you have a plant that you know that is under maximum transpiration, you can use it as the T-wet. If you have one that you know that is under severe water stress with no transpiration, would be the the T-dry, but this is really difficult to have, at least in the field. So what we do is to simulate that conditions. For example, in the dry references, we apply petroleum jelly to a leaf. In this case, we have garlic leaf. In this one, we apply petroleum jelly, so it would be the dry references. And in the wet one, what we apply we spray some water. So this would represent the wet reference. Of course, these are not real conditions or real temperature of dry and wet references, but they allow us to normalize for all the measurements. So what we obtain with this handheld camera is in the same image, the dry references, the wet references, and the leaf. We select the temperature or the target that we want. We separate it from the soil. So we calculate the crop water stress index. This is something that I used a lot during my thesis, but nowadays what I am using is the empirical based method that we need to construct this non-water stress baseline. So this formula, we need the delta T from the specific date that we are measurements. We need the lower limit, and we need the upper limit. So how do we construct the lower limit? We can see this graph. This is delta T values against BPD. So you can see how it changes, the delta T values, how it changes across different BPD values. These points are measurements of this apogee, of these infrared radiometers pointing to the canopies around solar noon in a range of 1.5 hours of 2 hours around solar noon. And we need to be sure that they were under non-water stress conditions. We knew that because we have these plots in an irrigated area that is irrigated to potential. So we know that those dates are under clear sky conditions with no stress and also around solar noon. So with that filters, you can construct these empirical lines to calculate the lower limit. So the lower limit is calculated using this formula that relates VPD with the delta T. So we have here two different non-water stress baselines because this can change between, in the trees, it can change with the age of the trees, or in herbaceous crop, it can change also in phenology. So you need to know how your crop works to understand these differences and apply the correct empirical line. The upper limit is calculated based also on experience. We have also measurements on severe stress plots, and we can see how the higher water stress is repeating one specific delta T. For example, in almond, we know that it's around 10 or 12 degrees Celsius. So this is a value that is repeated across the different measurements and is the maximum value of delta T. So once we have the lower limit and once we have the fixed value of the upper limit, we can calculate the crop water stress index just having the canopy temperature and the air temperature. This will be a setup of the empirical line method. We have here in a tower the apogees pointing to the canopies, one pointing to the soil for downward radiance. And of course, this is not a good day to measure. You can see cloudy. You can see that this crop was not still with all the leaves, but it's just a photo to see the setup. So we measure the canopy temperatures with the drone, and we measure the non-water stress balance with the apogee. So this makes some error because we are using multi-sensor. So one very important thing is the calibration and radiometric correction, especially if we are using different sensor for the index calculator. So what we do is a lab calibration seasonally. We measure each sensor, the drone sensor and the apogees, in a high precision black body. Then when we go to the field, we do temperature calibration with a portable black body, but also with these apogees, we measure the ground while the drone is flying. And then afterwards, we do the temperature radiometric corrections with the downward radiance and the emissivity. Sometimes people do not do that. This is for a very accurate and good quality data. But if you have the opportunity to have the downward radiance and the emissivity, it would be good to do it. So this would be a diagram of all the process. Maybe it seems like very complex, but once you have all the protocols and the steps, it's a step forward method that you can apply in all your measurements. So some results, I'll try to be a bit fast because it's been 20 minutes from now. We have validated this crop water stress index against stem water potential in almond. This was made with drone data, and they correlate very well. Also with high precision infrared radiometer with stem water potential. This is in another orchard. It works really well. Also with the drone data and the TSEF model. With gas exchange variables, one interesting thing that I did during my thesis is to correlate crop water stress index with the stomatal conductance, and it allowed me to separate not only water availability treatments, but it allowed me to separate cultivars' responses to water availability. That was very interesting to rank resilience among different cultivars and water availability. Also, it's important to do, as I told you, a multi-sensor comparison, because except the coefficient determination would be really good because you are measuring the same, the bias need to be into account when you want to scale up from one sensor to the other. Another interesting thing is to compare crop water stress index with other data that is not based on thermal data. For example, this one is our growth variability maps that are based on NDVI and reference evapotranspiration. We can see similar patterns. This is a plot that is irrigated equally, but we can see some intraplot variability. This was reflected in satellite data, but especially and more even clearly with the crop water stress index value, the same in other farm. We have used it also to assess almond yield. Was not bad at all. It was the fourth variable to assess almond yield, but some other indices, multispectral indices, work a bit better. But also, again, for garlic cultivars, we used to assess bulb biomass gains and to assess the differences of biomass gain between cultivars, and it was good enough to separate the behavior of these cultivars against biomass gain and again water availability levels. And one important thing is that thermal data is really, really good to assess plant water status because it's quite related with stomatal conductance. But if you have the opportunity, it's good to use also RGB and multispectral indices that can complement this kind of measurements. Because with some specific variables, as net assimilation or biomass gain, some multispectral indices would work better or would complement the results that you are obtaining with the crop water stress index. And I'm finishing just some decision support examples using thermal imaging. For example, in apple crop, a college of mine use metric, use thermal models to assess actual evapotranspirations with really good results. And this was used by farmers to irrigation scheduling. This is again the same images. Probably you cannot see here an irrigation failure. If you focus here, maybe in some part you can see an irrigation failure, but I'm going to do zoom in here. So crop water stress index, red values are higher crop water stress index, blue lower. Look, if I do the zoom here, we can see here some trees with a really high crop water stress index, but they are surrounded by lower values. So here, what occurred and what we see with the drone is a block in the dipper, okay? It could be a disease, it could be whatever. What we saw here is that surrounded by good values of crop water stress index, we saw this line. On the contrary, we saw leaks in the dipper with these crop water stress index values. So just to conclude, some take-home messages. It's important to move from the concept to the product. Thermal stress can be very operative, and we can translate it to use it for decision making. Each tool has its own advantages and limitations, so we need to be sure what is our aim, what is our target. Crop water stress index is very powerful, but the method must be chosen carefully in terms of what we need to check. And of course, thermal calibration is essential, especially when we are going to use different sensors. So this will allow us to have a consistency across different scales. So I don't know if I have time enough, if you have time enough, but if you have any question or comments, you can ask me now or use this email address to send me any comment or question. Thank you very much.